Welcome to today's Explainer. I'm absolutely thrilled to have you here today because we're going on a seriously cool factory tour. Have you ever looked at the literal miles of steel piping that make up our modern infrastructure and wondered, okay, how exactly is that made? Well, today we are going to dive right into how flat, incredibly heavy steel is completely transformed into flawless, high-strength pipe. And honestly, the most incredible part, it's all done using the invisible, immense power of electrical resistance. No glue, no filler metal, just pure physics and some seriously heavy machinery. Let's get into it. To guide us through the factory floor today, here's our roadmap. We're going to start by meeting the ERW process, move into shaping the steel strip, hit the climax with the high-frequency weld, cool things down with finishing and sizing, and finally wrap up with quality control and dispatch. All right, Section 1. Meet the ERW, or Electric Resistance Welding process. And as the subtitle says, there is absolutely no filler metal used here. Before we actually start the machinery, we need to define the real hero of our story right off the bat, and that is the scalp. So what's a scalp? Basically, it's the raw material we're starting with, a massive, flat, coiled strip of either hot-rolled or cold-rolled steel. The specific grade of this steel, whether it's low-carbon or high-strength, is carefully chosen based on exactly what the final pipe is going to be used for out in the real world. Okay, to really establish the sheer scale of this operation, let's trace the continuous path our scalp takes. Starting on the far left over at the uncoiler, it moves right through the forming rolls, directly into the ERW welding zone, then straight through sizing, and finally, it hits the cutoff point. It is literally one continuous, incredibly high-speed journey from a heavy coil of flat metal all the way to a finished pipe. Moving on to Section 2, shaping the steel strip through progressive roll forming. This is where we get to watch the raw material physically bend to our will. So the journey kicks off with preparing the raw material, and we are talking about colossal steel coils here, weighing anywhere from 10 to over 25 tons each. The coil is loaded onto a powered uncoiler and flattened out, and then a really critical step happens: edge milling. The outer edges of this flat strip are milled or sheared to remove any burrs or oxide scale. They absolutely must be made perfectly parallel to each other. Why? Well, because later on we need those edges to meet with a perfectly uniform gap for welding. If the edges aren't absolutely perfect right now, the entire weld fails later on. It's that simple. As that flat strip travels down the line, it passes through a series of contoured roll stands. Usually, this takes about 6 to 14 of these roll passes, depending on the exact size of the pipe. You can really see the progression here. Breakdown rolls do the initial edge bending, turning the flat strip organically into a U-shape. Then, the fin passes push those edges closer to the center line, closing it into an O-shape. Finally, it's prepped into a really tight V-notch profile just as it enters the weld box. Which brings us to Section 3, the high-frequency weld. This is the core step, and really the absolute climax of the manufacturing process. Now, what's genuinely fascinating is exactly what happens inside that weld zone. As the open tube edges pass through, they converge at a very precise V angle, usually just about 2 to 7 degrees. And positioned perfectly at the center is the impeder. This is a ferrite core rod sitting completely inside the tube. Its job is absolutely crucial. It acts almost like a magnet, precisely directing the electrical current so it travels exclusively along the very edges of that V-shape. This concentrates all the energy exactly where the weld point is. So the key here is the sheer amount of energy being directed by that impeder. The tube passes through an induction coil operating at a mind-boggling frequency, rapidly alternating between 100 and 400 kilohertz. That is incredibly fast. And because of that intense 400 kilohertz frequency being forced right along those thin steel edges, an enormous amount of heat is generated purely through electrical resistance. We are talking temperatures up to 1480 degrees Celsius. This brings the steel edges right to the brink. They become highly plasticized, sitting just barely below their actual melting point. With the edges practically glowing white-hot and fully plasticized, it's time for some brute force. Immense pressure from squeeze rolls physically forces these edges together. This forging action completely consolidates the weld into a seamless, flawless bond. And actually, as a bonus, that squeezing pressure physically expels any remaining oxides right out of the joint, pushing them up into what's called an upset bead. Remember, absolutely no melted filler metal was added here. The steel simply bonded with itself. All right, on to Section 4, finishing and sizing. We are now cooling down and refining the product. We have 4 major finishing steps to get through here. First up is scarfing.
Remember that upset bead of expelled oxides we just talked about? Well, while the metal is still hot and ductile, sharp carbide tools immediately scrape off both the external and internal beads, restoring a perfectly smooth, uniform wall thickness. Next is seam annealing. The extreme heat of welding can actually cause hardness peaks, which makes the steel brittle. So an induction coil reheats just the seam area to about 920 to 960 degrees Celsius and lets it air cool. This normalizes the structure and eliminates residual stress. Third, the pipe travels through a multi-stand sizing mill. This corrects the outside diameter to an exact tolerance of plus or minus 0.5% and perfectly straightens the tube.
And finally, the length cutoff. Because this entire mill operates continuously at speeds up to 50 meters per minute, you can't exactly just stop the line to cut the pipe, right? Instead, a high-speed flying cutoff saw dynamically clamps right onto the moving tube, travels alongside it, and chops the pipe to standard lengths completely on the run. This ensures production never skips a single beat. Let's move to our final section, Section 5, Quality Control and Dispatch. Time for those final checks where this pipe takes its final exam. Now, every single pipe must pass a mandatory, truly rigorous gauntlet of quality control checkpoints. It's not just a quick visual inspection for surface defects. They use ultrasonic testing to scan the internal integrity of the weld. They use hydrostatic testing, which literally means pumping it full of highly pressurized water to guarantee it won't leak under extreme strain. They meticulously audit the dimensions, run eddy current tests to check for seam continuity, and finally, they generate a mill certificate. This permanently documents the exact chemical and mechanical properties of that specific batch. Only after passing that gauntlet do we reach the true final step. The approved pipes are cleaned and surface treated based on whatever the customer needs. This could be a heavy-duty internal and external coating, galvanizing, or maybe just a simple varnish. Then they get uniquely stenciled with their heat numbers and dimensions, and finally, they are securely bundled with steel straps, completely ready for dispatch. The journey from a massive flat coil of sculpt to a meticulously engineered pipe is it's truly a marvel of modern manufacturing. So I'm going to leave you with this final thought. Next time you encounter the vital modern infrastructure all around you, whether it's water mains, structural supports, or pipelines, ask yourself, was it simply forged by immense heat, or was it flawlessly shaped by the invisible, high-frequency power of electrical resistance? Thanks so much for joining me on this explainer, and keep questioning the world around you.